Motion blur is a fundamental cue in the perception of objects in motion. This phenomenon manifests itself as a visible trail along an object's trajectory, being the result of a combination of relative motion and light integration. Thus, motion blur is the result of objects moving during exposure time. The amount of light entering a camera is limited by the diaphragm and the shutter, where the diaphragm defines size and shape of the aperture where light enters the camera and statically influences the amount of exposure of the film, depth of field and field of view. Shutters are devices designed to limit the exposition to a finite range of time. Once opened, and because the media integrates all light hitting its surface, several views of a moving object may be projected to different areas of the image plane. This resulting interaction between light, diaphragm, shutter, exposed media and object motion produces motion blur. Interaction can be formalized by this equation, where L omega represents the contents of the image plane in the direction of omega. Captured light is the result of the integration of the incoming radiance L during exposure time when the shutter is open for delta t amount of time. F omega t models the influence of optics, shutter, aperture and film. Images recorded using real cameras automatically incorporate motion blur. Even natural images seen by our eyes contain a similar effect called motion smear. This means that motion blur is actually something we would expect to find in any moving image. A sequence of images lacking motion blur can contain strobing artifacts, making the predictions of the human visual system difficult, and object trajectories may not be understood as continuous paths. Rendering algorithms discretize continuous signals producing different forms of aliasing as a side effect. Reducing temporal aliasing by avoiding time undersampling is the main goal of motion blur rendering techniques. In case of video games, motion blur is often used to increase the sense of speed. Most motion blur techniques require the scene to be rendered in a separate pass to generate a per pixel velocity buffer. Multi-pass approaches like this are very limiting because a lot of applications cannot afford to send a scene through the entire graphics pipeline more than once. However, motion blur can also be implemented as a post-processing effect, which improves efficiency but may also compromise the overall quality of the image. Most post-processing methods use one or several pre-rendered snapshots of the scene and blur them using motion information built from the images on object animation data. With such an approach, motion blurring and rendering methods are fully decoupled. This also makes the technique independent of scene complexity since it operates in image space. Our implementation uses a post-processing shader that implements image differencing and background subtraction in order to create motion blur. Image differencing works by using the reference image and this formula, and then you gradually change the value of each pixel in the reference image. R new is thus the resulting image you want with motion blur, and obtain that by multiplying the alpha value onto the old image, the previous one, and add that to the alpha of the current image. Image differencing can create ghost objects, which may or may not be desirable. However, in our case we're going to use the ghost images in order to create our motion blur effect. Ghost objects can be used to obtain the coarse movement, in which case the ghost becomes the trail of motion that follows the object.
I'm going to present our implementation of a post-processing motion blur effect through Unity Pro. We have this script here called CAM post-processing script and a shader called temporary or TMP post-processing shader. They're being applied through the original Unity way, in the same way that their own motion blur is. You can see that it's exactly the same variables. And I'm just gonna really quickly cover what's actually going on in here. So first of all, we inherit from the image effect base, which allows us to create image effects onto our camera as a post-processing effect. If I press F12 really quickly, you'll see that it has the shader and material and so forth. So that's already defined in there. Good. We have this float called amount to blur, which is effectively our alpha value, which is how much do we actually want to fade in and out of the two images that we're working with. Because our system works with having 2 frames. These 2 frames are then being applied onto each other via blurring through the alpha channel. We'll show that through this shader thing we have here. Good. So get texture is the texture that we actually apply onto the source texture on the camera. What you see right now is the source. The moment I start it up, it will apply the previous frame onto that, creating this trail that you're going to see right now. You see this trace, this extra thing that's being applied onto it, except for the extra blur that was just there because I forgot to disable it. We have this function called onRenderImage, which is being called every time the camera is pre-rendering the frame for the game video window. Good. We have this if statement here, which makes sure that the texture that we're trying to load into the destination, which is this one, which is, sorry, I forgot to explain this destination. The destination is the end of the road. When you load something into the destination, it gets loaded into this window, whereas the source is before it gets loaded in. So if we just take the source and put it into the destination, we're going to see basically just the standard without any effects or anything at all. Just the pre-rendered image from whatever's in the game. Okay, quickly again. This one makes sure that the texture we're trying to load into the destination and mixing with the source is not out of bounds with the actual source, so we won't mix it out with, say, we have a source texture of 2x2 pixels and an effect texture of 6x6 pixels. So we will always get the same. It will always be 2x2, both the get and the source, or whatever else it might be. Good. So it just destroys and it creates and does some other things. We have this function here called the graphics.blit, which is kind of the very important. It copies the source into the get texture and makes sure that the get texture is always the same as the source when we begin this computation. And go to amount to blur. Amount to blur here is being clamped between 0.0 and 0.92. 0.0 is because if it is 0, we don't have any blurring at all. The alpha value of the second texture will just be 0, and there will be nothing to see. If it is 1, it will be entirely, I think the term is opaque, entirely opaque, which means that you will only be able to see the second texture or the previous texture, which again means that there is no reason at all to go above 0.92 because you wouldn't be able to see the motion blur anyways. So we clamp between 0.0 and 0.92 in order to create the smooth motion blur, or be able to deactivate the motion blur at any given time. Then we pass in the main texture, which is our previous frame, which is the get texture that we got from the graphics.blit, and then pass that on into our shader. Here, as you see here, we have this property right here that's called main text. And the same thing with the alpha value. This time we just have this 1 minus alpha value because we want to invert the value and go from 0 to max and not from max to minimum. Good. Graphics.blit source, get texture, material. This function has a new argument, which means that it calls to the material and applies the effect that the shader will affect to this texture. And then after that, when it returns, it'll just load the get texture into the destination. Okay. We have the subshader with the tags Q and transparent in order to allow transparency in the shader. In the first pass, we set right off, lighting on, and blend source alpha 1 minus source alpha. This blend here makes sure that we can actually access the alpha value, and this one, set right off, makes sure that we don't occlude anything with our alpha value. We don't want the depth in there right now. Good. So the CG program's down, we define the vertex and fragment shader, and we include all the Unity specific variables and functions that we need. And we just define a quick function with the position and the texture coordinate that we need. Moving on to the vertex shader, which more or less just makes sure we know where the position is. It's in the vertex position is in the view projection, and the texture coordinate has been applied as needed. That's what this more or less does. Then we make two references to the properties. If we didn't do this, we wouldn't be able to access them in the fragment shader right here. So the fragment shader just works on the color, and it has a return type of a 4-dimensional vector, and we create a variable in here, of course, which is a 4-dimensional vector, and just apply the texture, which in this case is the previous frame that we want to apply onto the source texture. Good. So returning the value of the original color, which means the texture that we apply onto here, of the red component, green component, blue component, and the alpha value. So this is a 4-dimensional color vector of RGBA, and then that returns right here and gets loaded into the destination, at which point we can just see it in the system right here. So we press this one now. You can see how it motion blurs through the shader. If I went in here and just put this one and press this, and you'll see it all disappears. If I turn this down, you'll see the alpha value is on 0, so it's invisible, and you'll see up here that it's on max. If I was actually able to go above, you would see that it would stop, but I'm not going to show that because it takes too much time to show. Quickly, I'll also show the Unity Motion Blur just to compare. Again, if you go down, you'll see that it disappears. If you go up, you'll see that you have the very, very intense trail behind it. Yes, and that's it from us. Thank you for listening.